Hi everyone, welcome to my channel. In this video, I am going to talk about limits of rational functions. Let's explain limits of polynomial functions first. As x goes to infinite, consider this polynomial degree of 2. As x goes to infinite, as you see, we have three terms. This monomial degree of 2, this monomial degree of 1, and constant term. It's obvious that this leading term will be dominating 1 as x goes to infinite. That's why we may ignore other terms and we just focus on the x squared terms. In that case, we can directly obtain our result infinite square infinite. And consider next example. As you see, we have three terms. We may ignore this term and this term. We just focus on the leading term minus x cubed. As x goes to minus infinite, we have minus coefficient here, minus times minus infinite to power 3. So this is minus infinite because of this 3 odd power. And we can write minus times minus infinite, and the answer will be infinite. Okay, let's explain how to compute limits of rational function. Consider definition of a rational function. You are given two polynomial functions such as p of x and q of x. So division of those polynomial functions results in a polynomial function. Okay, let's investigate limits of rational function by some examples. Consider this basic example. We have this rational function 2 over x, constant term over x. As x goes to 0 from right hand side, we can write here 2 over 0 to the power plus. We may regard this notation as some number which is very close to 0 but positive 1. For example, you may choose 0 to the power plus as 0.00000 dot goes like that and 1. So when you substitute any number like that into this position, you are going to have sufficiently large value. Attention here, since x goes to 0 from right hand side continuously, we just write here infinite. And similarly, consider left hand side approaching to 0. In that case, we can substitute 2 over constant term over 0 to the power minus. So in that case, we may consider 0 to the power minus as a number like this, minus 0.00000, something like that. Okay, when you substitute any number like that into this position, you are going to have any number sufficiently small number like minus infinite. Okay, now let's explain these limits over this graph. In fact, when we consider the graph of y is equal to 2 over x, look at here. So this is 0 origin. When we try to approach origin from the right hand side, in that case, as you see, the corresponding output tends to be infinite. And when we consider, okay, the left hand side of this 0, consider input at the left hand side of 0 and consider corresponding outputs, as you see, we are going to have minus infinite. Okay, let's see another example. As x goes to 0 from right hand side, compute limit of this expression. When we directly substitute x is equal to 0 here, 0 plus 1 over, and consider this expression. And look at here, when we substitute 0, let me write here, 0 to the power plus square minus 0 to the power plus. Now we may consider this 0 to the power plus as a number like this, 0.00000, something like that. That is very close to 0 but positive 1. In that case, we can obtain any number. So this expression is very close to 1. And consider this expression. When you take square of 0 to the power plus, you are going to have a number which is smaller than this value. That's why we have 0 to the power minus. Namely, we have a number which is very close to 0 but negative 1. In that case, we obtain minus infinite. And what about other example? But as you see, we consider the same function, but in this case, we try to approach 0 from left hand side. Let's substitute a number which is very close to 0 but negative 1, not positive 1. So let me write here. So plus 1 over 0 to the power minus square minus 0 to the power minus. And attention here, the top is a number, the top is approaching 1, and consider this expression. when we consider a number like that, for example, minus 0 dot 0, 0, 0, 0, 0, dot, 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 something like that, as you see, we consider a number which is very close to 0, but negative 1. So consider this expression. In that case, we obtain a number, but the positive 1, which is very close to 0. Okay, in that case, we can directly write infinite. Now consider next example. So as x goes to 1, so the top is approaching 2, and consider the bottom 1 to power plus square minus 1 to power plus. What does it mean 1 to power plus? We may regard this 1 to power plus as a number which is very close to 1 but bigger than 1, something like that. So in that case, when we substitute any number like that into this expression, you are going to have a number which is very close to 0 but the positive 1. We can write this. So the answer will be infinite. Now consider next example, but in this case, we try to approach x, we try to approach 1 from left hand side. We just directly substitute x is equal to 1 to power infinite, 1 to the power infinite plus 1 over 1 to the power minus square minus 1 to the power minus. But in that case, we may regard this number as a sufficiently close, as a number which is very close, 1, but smaller than 1, something like that. When we substitute any number like that into bottom here, we are going to have a number which is very close to 0 but negative 1. And the answer will be minus infinite. Okay, consider limits of rational functions at infinites. As x goes to infinite, as you see, our function is a rational function given by the quotient of two given polynomial function. Consider the degree of top, it is 3, and consider degree of bottom, it is 3. Okay, now, so focus on the top. As x goes to infinite, so this x cubed will be dominating 1. That's why we may ignore this term, we may ignore this term, and we may ignore this term. And similarly, we may ignore this, we may ignore this, because of the fact that minus x cubed leading 1 will be dominating 1 as x goes to infinite. That's why we can directly write this limit as x goes to infinite. We focus on the x cubed at top, and we focus on the minus x cubed at the bottom. Before substituting x is equal to infinite, we just simplify this term, and the answer will be minus 1. And consider other example. Similarly, this leading term will be dominating 1, ignore these terms, and this term will be dominating 1, ignore these terms, and the answer will be directly by the quotient of these leading terms, and the answer will be 1 over 2 as x goes to minus infinite. Okay, let's see next example. So focus on this term, leading term. This will be dominating 1 as x goes to infinite, ignore this term, and this x squared will be dominating 1, ignore these terms. Let's compute limit of these leading terms, divisions of these leading terms, x cubed over x squared. We are going to have x, this and this simplifying. We got x, as x goes to infinite, x term is going to infinite. Attention here, degree of top is bigger than degree of bottom. Okay, and similarly, even if coefficient of leading term at top minus, again, we can obtain the same result. We may ignore these terms, and we just focus on the division of leading terms. We are going to have minus x when you divide x cubed and x squared, and as x goes to minus infinite, attention here, the limit of minus x will be minus x times minus x. The answer will be infinite. And look at this example. As x goes to infinite, these terms can be ignored, and these terms can be ignored. We just focus on x squared over x cubed. In that case, so we have x at the bottom. Let me write here, limit as x goes to infinite, we got x squared over x cubed, 1 over x. As x goes to infinite, we got 1 over infinite. The answer will be 0. Attention here, degree of top is smaller than degree of bottom. That's why limit will be 0 as x goes to infinite. And similarly, as x goes to minus infinite, we got the same answer, 0, in this exercise. As you see, degree of top 3, degree of bottom is 4. That's why the answer will be 0. By ignoring these terms, we can find out this result. See you next time.